Hello and welcome to this video on flat stationary Earth. Is the Earth flat and stationary? Now this is possibly one of the most controversial experiments that you'll come across that actually has a very good possible proof that the Earth is flat and stationary. Now I know you people have been after me for ages to do another forbidden experiment. So this is probably a perfect forbidden experiment because it is very controversial. You won't know anything about it, and it fits exactly in with our gravity Cavendish experiments that I've been on and our Foucault pendulum experiments. So it sort of fits in the middle of that. So that's why I've sort of inserted this little experiment in the middle of all our main gravity experiment that we're in the process of doing. Now, the experiment's called the delta T experiment. And it basically goes like this. 1687, Isaac Newton discovered this mass attraction and formulated our first concept of gravity started to form. 1793, John Michell dies. Strange. John Michell was the inventor of the famous Cavendish torsion experiment that you'll see everywhere, done to death in all physics textbooks. John Hyde Wollstone took Michell's experiment and he gave it to Cavendish. In 1797, Cavendish did his famous density of the Earth experiment to prove the Earth was, to work out the density of the Earth. And during this period here, we didn't know whether the Earth was spinning or turning or round. It wasn't conclusively proven until 1851, when Foucault, as you know, my experience with Foucault, proved 100% that the Earth was round and spinning, which was knocked on the head, definitely sort of nailed completely in 1905 by Einstein. So, the Cavendish experiment, the density experiment. Weird. We already knew the Earth was between 2 and 3 tonne. They knew the size of it. So a cubic metre was, they knew this weight roughly would be this. They knew the size of the Earth. Really, density was that important? Now, maybe Michell wasn't doing a density experiment. He was an autodidactic. These two guys here were members of the club and the Royal Society. So, okay. Enough of that. Let's go on to the delta T experiment and see what that's all about. Alright, so what is the delta T experiment? Basically it's this. If we have a plumb bob on the spinning ball Earth, there'll be two vectors involved with establishing the stability of this plumb bob. Firstly be the attraction to the centre of the Earth, a massive vector, and there'll be a slight small centrifugal vector pulling it out. So a resultant vector, this green vector, will be somewhere in the middle here. And this is well established. So on a flat Earth, flat stationary Earth, there'll only be one vector involved, this downward vector. You won't have this centrifugal vector. So what we do to determine the delta T experiment is we take a plumb bob and we place it in a vacuum tube, a cylinder of probably 6 metres long or even longer, and we use at least a 1 metre, 2 metre long plumb bob, and we measure the oscillation of the plumb bob. Now it'll oscillate back and forth in a period which will be determined by delta T in time, change in time, which will be dependent on the torsion of the suspension cable and the friction of any bearings or any hanging devices that will determine how much it swings. Now, what the controversy is with the delta T experiment is if there was a centrifugal vector, the plumb bob the bob part should actually turn and swing and stabilise to the centrifugal force. And in theory, well in practice, the laser should not oscillate. However, the laser oscillates. Now you'll see this in my experiments, you'll see this in every Cavendish experiment where you'll see this oscillation going back and forth. It'll be a certain period in time. Some will go fast, some will go slow, some will go really slow. Now you've seen my experiments and the Cavendish experiments were going extremely slow with this pendulum. This pin pendulum number 4, which has another laser on the bottom, which you will use that later on. Now that's what the controversy is with this so-called, I guess, the delta T. I have to play the devil's advocate and I have to tell you about it. And was Michel actually trying to look for the spin of the Earth rather than the density of the Earth? So no one can prove, I can't prove it 100%, but I'm just throwing it in there because it's an interesting experiment and we'll be introducing it because I'm about to do it with my Cavendish experiment. We have to stop this oscillation to do any critical measurements. So I guess that's where we're up to, and my next experiment will be continuing on from Cavendish experiment, and as I said before, this is just a short insert to help you people out who've been on my case about forbidden experiments. And I believe this is a forbidden experiment, and Michel died. He didn't get to do the experiment. Alright, enough of that. See you in back to this Cavendish experiment. Thanks for watching. Alright. Our swing deviation now is settled down, looks like. Hello and welcome to part 3 of our gravity and the Cavendish experiment. Today's experiment will be using a car battery as one of the masses. There's quite a bit of controversy about electrostatic forces, magnetic forces, currents in the masses that approach the Cavendish experiment.